Hey class, so this will be the last video in this section of notes. And so it's going to be about isomorphisms and a little bit more. So I don't really like the way the book does isomorphisms before it does homomorphisms. Just to me, it doesn't make sense. So first I'm going to start with homomorphisms. So a homomorphism is a map between groups. So we'll have one group, which I'll call G. And then here, I'm going to use slightly different notation than in the book, but we do have two different groups, so it's maybe, G. It's maybe useful to, I keep writing the wrong thing. It's maybe useful to subscript these things to indicate that this is the identity of G, this is the multiplication of G, and it's going to be mapping to a group here, which is H, and so this will be the multiplication of H, this will be the identity of H. Okay, and the properties are that that the operations are preserved and the identities are preserved. So first of all, we need that phi of the identity is the identity. And we need two, that phi of G, and then here. Now, later on, we'll stop writing all these subscripts, but then you have to keep in mind where the different objects are living, right? So here I'm going to write, G times G prime, right, is supposed to be phi of G times, now phi of G is in H, right? So this is going to be the product of H, phi of G prime. You might think that it's necessary to have inverses preserved too, but actually once we preserve the identity and we have this, we'll get that inverses are preserved. So let's just check that out. So we have that phi of, how do I want to do this? I guess I'll just do it like this. Let's see, I'm trying to think, I didn't really prepare this. Let's see, so I'll have E of H is equal to phi of E of G. It's one of our assumptions here. And that is equal to phi of G times G inverse. Now, yeah, okay, I'll make a comment on that later, but this is equal to phi of G times phi of G, phi of G inverse. Okay, and I could turn this around, right, into sort of in the other direction, right? So, so we'll also get here that E of H is equal to phi of G inverse times phi of G. And see, I'm not putting the, whoops. Let me just decorate these things a little bit. So this is in H, this was in G. Here I'm saying this is in H. And I keep doing that, phi of G. Right, so let me just rewrite this here. So we have those two things, right? And, this is one of those situations where this guy here, well, it's behaving like an inverse to phi of G. And so it is an inverse because the uniqueness of inverses, right? So we know that if we have something that acts like an inverse in the sense that if you multiply on the left and right by it, we get the identity element, then it is an inverse, right? So these two things together tell me that phi of G inverse is in fact phi of G inverse. It's not for free, we had to prove it, right? This will become more important when we're dealing with rings later to think about when this happens and when it doesn't happen. We definitely needed both of these things for that argument to work. Okay, so just keep that in mind. And I'll mention it again when we get to rings. But anyway, that's what a homomorphism does. It preserves the operations, it preserves the sort of main objects, right? In this case, the identity. And that's what a homomorphism is, okay? And you've seen homomorphisms before. So, in linear algebra, you study linear maps, right? So there, a linear map was a little bit more than a group, right? So we have some linear map. We have a vector space. Now here we could do the same thing. We have the plus in the vector space. And we have this kind of funny, scalar product. It's a little bit sort of a funny thing because it's actually a bunch of different products for every scalar object. But I'll just call it phi v. But it's it's not a binary operation. It's like alpha times v, right? So V, where this is a vector and that's a scalar, right? So I mean, it's a little bit funny for vector spaces. And this could be going to some W plus W and the scalar product in W, right? So like that. Oh, and sorry, there's actually just, sorry, let me add a little bit here. Because there is actually a, okay, well, there's a zero, remember there's always a zero vector, right? And so this would be going to, W plus W times W, 0W, right? Now, very often you don't write the two, W and V, but, it's sort of clear. I mean, this might be R5 and this might be P4 of X or something like that, right? So there's all sorts of, linear maps you looked at. But, this is preserving the structure. So it's preserving the group structure, right? And it's preserving all the group structure, which involves the V, the plus, and the zero, right? And it also preserves additionally, right, preserves the scalar product structure too. So, you do linear maps, it's even a little bit more than a group homomorphism. Good, all right. And we're going to learn a lot more about these because we're going to study their, so, I mean, just for a couple of quick things, if phi is going from G to H, okay, now I'm going to drop the subscripts, okay, so you have to just get that in your head by context, are we working in G? Are we looking at phi of something? Are we in H? Where are we actually at? We have that phi of the whole set G, right, which we might also call the image of phi. This is a subgroup of H, okay, so that's an easy thing to show. Let's just show it, okay, so how do we show it's a subgroup? We need to show that, so what am I saying is it's like this, right, or this, right, so these are the same, this just says apply phi to everything in G. So if I take two things in there, right, so I take, H and H prime in phi of G, right, well, what does that mean? It means that H is equal to some phi of G, and H prime is equal to some phi of G prime. It doesn't have to be unique, right? So just keep that in mind. I mean, it could be more than one thing gets sent to H. One thing can't be sent to more than one H, but it can be two things can be sent to H. And then we're going to have, then what do I need to show? I need to show that H prime is inside of this thing, right? But I have here that phi of, so H prime times H prime, this is going on in H, right, is equal to phi of G times phi of G prime. Okay, so this is going in H is equal to phi of G times G prime. Okay, this is going on in G, right? Yeah, okay, but this thing, right, is an element of this, right? So it's in phi of G. That's all I need to show, right? So H times H prime in H, right, is in phi of G. So I showed that phi of G is closed under products, right? So that's one thing we need to show. And we need to show that, we need to show that EH is in phi of G. But that's clear because, part of what we're assuming is that, EH is phi of EG. So clearly that's in phi of G. Okay, so that's a subgroup. That's an important subgroup. Again, just like with linear maps, the image of a linear map was always a sub vector space, right? The other one is the kernel. Again, also something you studied in linear algebra. Not surprising. I mean, these are common notions. So the kernel of phi is the set of all things in G that map to the identity. So phi of G equals E, right? And so here, this of course is the E of H, right? Because this is phi of G is in H, not in G, right? And this is also a subgroup of H, right? And so, oh, sorry. No, not at all. This is a subset of things in G, right? This is a subgroup of G, right? So let's just see why that's true. So suppose I have G and G prime, which are in the kernel. Well, then I know that phi of G equals E. This is E in H equals phi of G prime, right? So I know that phi of G, G prime is equal to phi of G prime is equal to E in H times E in H, which is equal to E, right? So G times G prime also gets sent to E, right? So we have closure. I took two objects in in the kernel, and their product is in the kernel, right? So that's one part of this, and the other part is that. So I need to show that E of G, right? So I'll just promising to stop writing the extra subscript. So E is in the kernel of phi. Okay, now this of course is the E of G, not the E of G of H. But that's clearly true because, phi of E is equal to E. Okay, now this is really confusing, right? This is the E of G, this is the E of H, right? So you just have to keep that in mind. And you're used to doing that. When you have a map going from phi, in the vector spaces from Rn to Rm, right? You say phi of 0 is 0, but they're two different zeros, right? This is a n-dimensional 0, this is an m-dimensional 0. So they're not the same even in that case. Okay, so little review of like subgroups. Good. Okay, so you can have various, if phi from G to H is a homomorphism, so preserves the structure. And then we can have phi is injective. Then we call it a epimorphism. Phi is an endomorphism. Sorry. Actually, I'm going to pause this. Can I pause? Yeah, I'm going to pause this for a second and look up my words. Okay, so I'm not finding, my brain was freezing there because actually there doesn't seem to be a real word for an injective homomorphism. So it's injective, right? Nothing else to say about that. If phi is surjective, there is a word for this one. It's called an epimorphism. Whoops. Okay. If H is G, right? So phi going from G to G, right? So in other words, H equals G, right? Then phi is an endomorphism. Okay, so lots of fun words here, coming from my Latin, Greek, I'm not sure. If phi is 1-to-1 and onto, this is an important one. This is actually what this chapter was about. If phi is an isomorphism. Okay, and two isomorphic structures are essentially the same structure, just except for the way we're labeling things, more or less, right? So they're basically, you consider it the same. So, two things, things being isomorphic is a equivalence relation, and we tend to just collapse those equivalence classes and say that's what it is, right? So that's the reason we say things like Cn and Zn are the same, right? Those cyclic groups is the same as any cyclic group, with order n. And that's not literally true. We sort of view them all as being the same. And the other important one here is if phi is from G to G. So again, if G equals H, is 1-to-1 and onto. So this is another really important one. 2, then phi is an automorphism. Okay, and I guess an important thing here is that aut G, this is something we'll look at a lot, is the set of all phi from G to G. Phi and automorphism. Is a group, is the automorphism group. So this is an important one. We'll look at it a lot later on, especially toward the end of the class, and we're doing more with rings, but it's going to be an important one. Good. Okay. So like I said before, just for some context, Zn is isomorphic to Cn, is isomorphic to R, right? Where the order of R equals N, right? And the isomorphisms are kind of clear. Now you have to be careful, right? This is usually we usually write this one as multiplicative. This one's usually multiplicative, right? So you're taking the zero or the identity, right, and you're mapping it. In this case, Cn, you're mapping it to, maybe we view that as being one, right? So typically we think of this as multiplicative, or here you think of it as being e, right? So you're mapping this to e, right, where this is sitting inside of some other group. Whatever the identities are, right? The identity has to map to the identity. Now that's not the only isomorphisms here. We can map any generator of Zn to any generator of Cn, right? Or any generator of this thing. So suppose we're in Dn, and we're looking at R, right? The rotation, right? So we know that the order of R is n, right? We know that R to the n is equal to E, right? If I take M such that GCD of M and N is equal to 1, right? Then we know that Rm equals to R. This is part of what we did with cyclic groups, right? Above, right? So we know that it generates everything. And so the map, 0, 1 maps to R, 0, 1 maps to Rm, right? R maps to Rm. These are all things, right? I can map a generator to a generator, right? And that will still generate the whole group, and all the structure will be the same. So here I map, if I'm trying to map, for example, if I just want to look at automorphisms of the cyclic group, right? I can map R, which is a generator, to any Rm, right? Where the GCD of M and N is equal to 1, because that'll generate everything. All right. Or I could map, the 0 of Zn to either one, to any Rm, right? Or I can map the 1 of Cn, etc. Right? I guess I'm viewing Cn. I'm not really sure what I want to say this is. I guess I'm sort of thinking of going from 1 to 2, N back to 1. But I don't know, maybe you could also think of it as being the nth roots of unity in the complex numbers. I mean, there's lots of representations of, these common things. So those are all isomorphic. Z itself, right? Z is isomorphic to any cyclic group that's got where the order is infinity, right? So, this group is given by GI, right? For I and Z, right? And in this case, there's really only one thing you can map. There's only one generator here, right? It can only be G, right? That's the only thing that can generate this whole thing, right? So, one has to map to, let's see, is that literally true? I guess it could be G or minus G, right? So I guess that's actually important, right? It could be plus or minus 1. So plus or minus 1 gets mapped to G, plus or minus 1, right? That's the only way that map can go. Good. That's the point, right? Minus 1 is also, so there's two generators in Z. There's 1 and minus 1, right? So those two generators can map to either of those two generators. And this is actually important for the DNs, right? So the DNs, I've sort of focused on this a little bit. These are typically given by a presentation. They're given by generators, some R and F. I think I usually call it F for flip. I think maybe something calls it S, right? And these are given by Rn equals E, F2 equals E, and then one of these guys, RF, RF, or FR, FR, it doesn't matter, equals E, right? So one of those two things. So these generators completely determine DN. I mean, any other fact about DN can be proven from these things. And so that's the sense in which this completely characterizes what DN is. And so if I have any two sort of representations of DN, I can take this R and F and map it to any other R prime and F prime where this is some other flip. This thing would have to be a generator of the whole group. So literally the map would be R goes to any RM where GCD of M and N is equal to 1, right? F can map to any other flip, and all the flips are going to be of the form RMF, right? And those would all be automorphisms, right? And if I map to something that wasn't a relatively prime like this, then you would be mapping to a DM, right? Then maybe its order would be M, and you would be getting basically this would be collapsing down to a DM instead of a DN instead of DN, right? So really important to understand the generators because that can completely determine how mappings go. Let's see. So automorphisms. Let's see. So I've talked already about. Well, I guess one thing about vector spaces, right? How do you get automorphisms of vector spaces? You just same like generators, right? You just map a basis to a basis, right? And that's how you get automorphisms of vector spaces. So vector spaces are really nice. They're really easy to generate maps for. And actually, you can get maps really easily. You just take a basis and map to anything, right? And that'll give you a homomorphism. You just map to anything. Take a basis, map to anything, and then extend by linearity, right? So that should be common. That should be something you know from linear algebra. Let's see. Given a group G, there's a specific set of automorphisms that are nice called the inner automorphisms. So these are the ones given by G gets mapped to. Actually, let me do it like this. So I'm mapping. Yeah, I want to match this notation. So G is an element of G, right? I'm taking some arbitrary H and I'm mapping to. I just want to match this exactly to G H G inverse. Right? That's the map. And so this map here I'm going to call phi G, right? And let's verify some properties of this. Let's verify that. Let's see. I'm looking at my own notation here. Let's verify that phi GH, right, of K. Okay, so now I need two things. So this is going to be GHK, GH inverse. Right, now we do an inverse, we flip things around, right? So this is GHK, H inverse, G inverse. And I've dropped all the parentheses because we have associativity, it doesn't matter, right? But now I'm going to add those back in like this, right? And what you see is this is actually phi of G, phi of H of K, right? So this is actually phi of the composed phi of H of K, right? Like that. And so we actually see here is that the map, if I take phi of G, right? So this is for every G and G. Sorry, for every little G and G. And I map it over here to, sorry, that's not what I want to say. Whoops. Come on. Eraser, please. Okay. I'm mapping G gets mapped to phi of G, right? So I guess that was kind of in the notation. This is actually a map from G to aught G, right? So G is sitting there. And by the way, these, well, okay, let's show this, right? Let's show that, let's show here that phi of G is equal to the identity, right? If and only if G is equal to E, right? So I'd like to see that. So how can I do that? So so I have that phi right. So I have right. So suppose that phi of G is equal to the identity. So I want to show that G is equal to E, right? So phi of G is equal to H. Phi of G of H is equal to H, for all H. All right. So what am I doing? I'm assuming this side, right? And then I want to prove that G is equal to E, and I guess I should go the other way around too. But the other way around is kind of trivial. But here I can do, so what is this? Well, this is G inverse has to be equal to H, right? So that's what this is saying. But if I put G in there, right, then I get G inverse is equal to G, right? And I can cancel G's from both sides. Let's see. Well, let's see. Let's see. No, I'm not quite getting what I wanted here. Hold on just a second. Okay, I see. I got myself confused. So, well, okay. This is not what I wanted to do. But what I do get here is I get G inverse, right? It has to be E, right? Now, of course, on this side, right, I can get rid of that E and I can put those together. I'm still not getting what I want. Hold on just a second. Sorry, actually, I'm not proving this because it's not true. This is not what I want to say. Let's actually look at this a little bit. I actually even have a comment about this down here. Suppose phi, suppose phi of G is equal to the identity, right? So what am I actually looking at there? So this is a map. This map here from G to phi G. Let's call this thing here phi, right? So it's mapping G goes to the map phi G. This is an automorphism, right? This is an aut G. Oh, by the way, what's the operation here in this group is composition, right? I guess I didn't mention that above. It seemed clear, but maybe that's not so clear. But suppose it's true, then what I know is that for all H, phi of G of H equals H, right? So that turns into G inverse equals H, right? For all H. All right, but this says specifically that G is in a group called the center of G, right? So the center of G is, so G is in the center of G if and only if exactly this, right? So for all H, G inverse equals H. I mean, that's definition, right? And actually earlier in the notes, I didn't talk about this in the last one, but I don't think I did. Where was it? Actually, it was up with here, right? There's a little bit about, no, what was it? A little bit about centers. Sorry. Was here. The subgroup. Oh, it's actually part of topic 1, right? Sorry. Yeah, there's a little bit about centralizers and centers. I forget now. Maybe I did talk about this, but there's a little bit there, right? So those are subgroups. These are sort of typical subgroups. Let's see. Now I'm down here again. Come back down here. Anyway, the point is this, that phi of G is the identity map if and only if G is in the center, right? So we're actually getting here is, and so what does this mean? This means that phi of G, sorry, nope, it means that G is in the kernel of this map phi, right? So this map here. So I'm mapping G goes to, so G is getting mapped to the automorphism phi of G, right? The kernel of that map is actually ZG, right? So what we've proved here is that ZG is the kernel of this map that I'm calling phi here. So it's actually that. So we'll see next time, this is jumping the gun a little bit too much, but we will see that G, what is the image? Let's think about that real quick. What is the image of phi? Well, this is the set of all phi of G for G and G, right? So all of those automorphisms of G, which happen to be these inner automorphisms, so the ones that are just G inverse, right, that are defined like that. And so this group is called the set of inner automorphisms. This is inner in G, right? And what we've proven here, well, what we will prove at the end of next time is that in G, right, is isomorphic to G mod ZG. Okay, so that's actually what we'll prove. Oh, go ahead. I mean, that's sort of what we have proved, but we need something called the isomorphism theorem. First, I guess the first isomorphism theorem to say that fully.